Hello students, welcome to my channel Arun's Physics Portal. In this lecture, I will discuss about the Hurwitz test for circuit stability. This topic is meant for MSc Physics and Electronics students and also for BE and BTech students of EEE and EC branches. The research scholars pursuing research work in electronics will find this topic useful. This topic is also useful for GRF and NET aspirants. The complete note of the topic is given here for your convenience. I hope you enjoy going through it. Now let us come to the topic. In an earlier lecture, we have seen what is the meaning of circuit stability. The circuit stability refers to a circuit's ability to maintain its desired behavior over time without oscillating or producing unwanted signals. In control systems and electronics, stability means the circuit doesn't produce oscillations, it doesn't amplify noise excessively, and returns to its steady state after initial disturbance. We have seen Routh-Hurwitz stability criteria. In this lecture, we will discuss about the Hurwitz test. This is another way of testing the stability of a circuit. We have seen that the transfer function of a circuit can be expressed as Ns equal to Ps upon Qs, where Ps and Qs are two different polynomials of different degrees. Let Qs be expressed as the sum of two polynomials, that is Qs is Ms plus Ns, where Ms contains only the even power terms and constants and Ns contains only the odd power terms. We now form a new fraction phi equal to ms upon ns or phi equal to ns upon ms, such that the numerator polynomial is of higher degree than the denominator polynomial. Assuming that ms is of the higher degree than ns, we can write phi equal to ms upon ns equal to a1s plus r1s upon ns, where the remainder r1s is an even polynomial of degree 1 less than that of ns. We now divide ns by r1s once to get ns upon r1s is a2s plus r2s upon r1s. This process of division is continued with successive remainders like this. R1s upon r2s is a3s plus r3s upon r2s, r2s upon r3s equal to a4s plus r4s upon r3s, and so on and so forth. The degree of the remainder polynomial goes on decreasing with each step, and finally the procedure terminates. We now examine a1, a2, a3, a4 and so on. If all of them are positive, Qs is a Hurwitz polynomial and the system is stable. If any of the coefficients or the a1, a2, a3, a4 is 0 or negative, Qs is not a Hurwitz polynomial and the system is unstable. We illustrate this procedure by means of the following example. Let Qs is equal to s to the power 4 plus 4s cube plus 7s square plus 8s plus 2. We now divide Qs into two polynomials, ms and ns, where ms contains all the even power terms and ns contains the odd power terms. And we divide ms by ns. So this gives you s to the power 4 plus 7s square plus 2 upon 4s cube plus 8s. By actual division, we get this equal to 1 by 4s plus 5s square plus 2 upon 4s cube plus 8s. We divide then 4s cube plus 8s by 5s square plus 2. So by actual division, we get 4 by 5s plus 32 by 5s upon 5s square plus 2. Next we divide 5s square plus 2 by 32 by 5s. This gives us 25 by 32s plus 2 upon 32 by 5s. And finally, we divide 32 by 5s by 2 to get 16 by 5s. So we find that A1 is 1 by 4, A2 is 4 by 5, A3 equal to 25 by 32, and A4 is 16 by 5. As all A's are positive, QS is a Hurwitz polynomial. So another situation may arise if QS contains a factor that is an even polynomial. In that case, both MS and NS will have this factor, which will then cancel out. But it may not always be obvious that such a factor exists. If such a common factor exists, then it will be carried through and will appear as a factor of each remainder. We will state this by the following example. Let Qs equal to s to the power 4 plus 2s cube plus 2s square plus 2s plus 1. We divide this Qs into two polynomials, ms and ns, where ms contains the even power terms and ns contains odd power terms, and we divide one by the other. So phi equal to ms upon ns. So this is s to the power 4 plus 2s square plus 1 upon 2s cube plus 2s equal to half s plus s square plus 1 upon 2s cube plus 2s. We now divide 2s cube plus 2s by s square plus 1. The numerator can be written as 2s into s square plus 1, and the denominator is s square plus 1. So we find from here that s square plus 1 is a common factor in both numerator and denominator. When solved, this gives you 2s. So we find here that a1 is half and a2 is 2. We see that although both a1 and a2 are positive, the division process terminates prematurely, as the last divisor s square plus 1 is not a constant. Since s square plus 1 occurs as a factor in both ms and ns, s square is a common factor, which is an even polynomial. We now consider the implication of an even polynomial factor. An even polynomial is of the form es equal to s to the power 2k plus a 2k minus 1, s to the power 2k minus 1 plus so on and so forth plus a2 s square plus a naught. हम सबसे सिंपल पॉलिनोमियल की बात करते हैं, इवन पॉलिनोमियल. So that is your s square minus a square is 0. This gives you the solution as s equal to plus minus a. So if we have a root in the positive half of the S-plane, we have another root of equal value in the negative half of the S-plane. Clear? So the roots are plus a and minus a. Okay? It follows that if S0 is a root of ES, then minus S0 will also be a root of ES. That is to say, an even polynomial ES has roots in both the halves of the complex plane. We have seen earlier that if a polynomial has roots in the left half of the S-plane, the system is stable. And if the roots lie in the right half of the S-plane, the system is unstable. एक ही तरीका है कि हमारा ES जो है सो इवन पॉलिनोमियल है और राइट हाफ इस प्लेन में रूट्स नहीं हैं, तो एक ही संभावना है कि हमारे रूट्स जो हैं सो जी ओमेगा एक्सिस पर हों, which also leads to instability. Clear? We thus conclude that if the Hurwitz test terminates prematurely, or if any of the A's is 0 or negative, QS will not be a Hurwitz polynomial and the system is not stable. In other words, if the Hurwitz test does not terminate prematurely And if all the A's are non-zero positive quantities, then QS is a Hurwitz polynomial and the system is stable. Clear? So this is all about the Hurwitz test for testing the stability of a circuit. I assume you like this presentation. यदि आपको मेरा यह प्रेजेंटेशन अच्छा लगा हो तो इसे लाइक करें, शेयर करें और मेरे चैनल को सब्सक्राइब करें. So thank you for watching. See you next time with some other topic of interest. Till then, goodbye.